Thank you very much for the kind introduction, Vladislav. Good afternoon, everyone, and welcome to my talk. Of course, I would like to thank the organizers for inviting me. It's a great pleasure. And yeah, let's start. Here's the outline of my talk. I will start with a brief introduction on the topological insulators, although Vladislav has given a very good insight into these materials in his talk. I will just briefly recall what are those materials, and I will spend quite a time talking about time reversal symmetry breaking in TIs. And then I will introduce antiferromagnetic TI state of matter, which is a new time reversal symmetry breaking phase. Later, in the core of my talk, I will present our results on prediction and experimental confirmation of the first antiferromagnetic TI, which is manganese bismuth 2-tellurium-4. And before I conclude, I will briefly review the current status of this emergent field. So let's start. In 3 dimensions, a non-magnetic topological insulator is a material which has an insulated bulk, but almost necessarily a metallic surface. Why does it happen? Because of the spin-orbit coupling. So let us consider this on the example of bismuth selenide, which is a model TI. Here is the structure of this material. So what happens, basically, it turns out to be located near the gamma point of this material. Without spin-orbit coupling, the valence band maximum is mostly contributed by selenium atoms, while the conduction band minimum by bismuth atoms. Then you switch on the spin-orbit coupling, and this sequence gets inverted, as it is shown here. So this is what we call bulk band-gap inversion. And there is a theorem that says when the bulk band-gap of an insulator is inverted due to spin-orbit coupling, its surface will host a gapless metallic state. This is how this state looks like in angled Rutherford emission spectroscopy. You see that it has linear dispersion, therefore we often call it Dirac cone. And this is how the calculated topological surface state looks like. Although, okay, the peculiar property of this topological surface state is its helical spin texture. You see that for each state, the spin is locked perpendicular to the momentum. This is actually due to the time reversal symmetry, which protects the electrons from the backscattering, as is shown here, because to backscatter you have to flip the spin, but since we don't have magnetic perturbations, it is prohibited. Although it is time reversal symmetry that protects the electrons, people are actually trying to break this symmetry. So let us consider why and how. Basically, you can do this in 2 ways. You can introduce the external magnetic field, which is actually not very practical. And alternatively, you organize magnetic ordering, in which case the out-of-plane easy axis is interesting because it allows you to split the topological surface state by introducing this so-called Dirac point gap. Once you have realized that, you can try to observe a number of exotic and practically relevant effects listed here. For example, quantum anomalous Hall effect, which can be observed in the 2-dimensional time reversal symmetry breaking systems generally with a non-zero magnetization. The material's band structure should feature this inverted bulk band gap, and therefore, due to the bulk boundary correspondence, its edge should host 1-dimensional chiral mode, meaning chiral that at the given edge it can only propagate, the electron can only propagate toward one direction, it cannot backscatter, as is shown here. On the left we go forward, on the right we go backward. The quantized observable in the effect is the Hall conductivity, which is quantized to E²/h, and this C factor is the topological invariant, which is called first Chern number. It is basically the number of these chiral H modes in the sample. Another interesting and promising effect is the topological magnetoelectric effect. Imagine a 3D topological insulator film which is completely gapped due to the magnetism or magnetic confinement. In this case, if you apply an external electric field to your system, it will respond with an additional contribution to the magnetization, which is quantized in E²/h as well. And vice versa, by applying external magnetic field, you will get a quantized electric polarization. To get the effect, you gap the topological surface state, you place the Fermi level here, and starting from certain thickness, you will enter the quantized regime. And then you can try to realize such thing as image magnetic monopole, or another other consequences like topological magneto-optical effects, People have been trying to realize those in particular, and they have been successful in the non-magnetic TIs, but under external field. But this has not been possible so far for the truly magnetic TI. So let's see how do we create a magnetic TI. The first and the most, let's say, simplest way is the bulk doping. You try to introduce the magnetic dopants through the whole volume of the film. This method has already worked out because the quantum anomalous Hall effect has already been observed back in 2013, but at extremely low temperature of 30 millikelvin. Now the current record is about 2 Kelvin, which is achieved in this so-called modulation doped chromium BST. But actually there is a fundamental difficulty with these systems going higher in terms of the observation temperature, because you see they are intrinsically disordered materials, starting already with a non-magnetic system, and then you increase this disorder because chromium atoms are distributed randomly. Shown here is the surface map of the Dirac point gap acquired by scanning tunneling spectroscopy. You can see that this gap, or its value, better say, goes all the way down from its maximal value of 50 to 0. And zeros are here, and basically it is there where you disrupt the quantum anomalous Hall effect because your bulk, your two-dimensional bulk, becomes conducting. Other problems also exist because these materials have been found to show superparamagnetic behavior. Therefore, magnetic proximity effect has been considered as a viable alternative. In this case, you try to induce a finite magnetization in a TI through the interface coupling to a magnetic insulator, which is trivial. Many systems have been studied. European sulfide bismuth selenide has been probably the most controversial interface, most interesting one, because on the one hand, the room temperature proximity effect has been reported some 5 years ago, but actually very recently, as studied by XMCD, no magnetic proximity effect has been detected at such interfaces at all by Valenzuela's group. On top of that, if you calculate the electronic structure of such systems, you will see that apart from the Dirac cone, which is gapped, but not by much, you will have trivial interface states. They render system gapless, therefore useless for any kind of topological quantized effects. As a big surprise to me, a couple of years ago we learned about quantum anomalous Hall effect in such a proximity type heterostructure. Actually, I thought that this kind of materials will be useless for quantum anomalous Hall effect, but as you see here, this material is actually not an intrinsic magnet. It's diluted magnetic semiconductor. Therefore, it suffers from the inhomogeneity issues as well, and this is reflected in the low observation temperature. Obviously, we needed alternative approaches to combine magnetism and topology, and one of them might be antiferromagnetic topological insulator. It was conceived about 11 years ago by Monk, Essin, and Moore, who suggested that it can be realized in the insulators breaking both time reversal and primitive lattice translational symmetry, but preserving their combination, which gives rise to the Z2 topological classification. Shown here are 3 examples of the two-dimensional antiferromagnets that can meet or not, this symmetry, but I will show the material-specific example in what follows. Pretty much as the time reversal symmetry in ordinary TIs, the combined S symmetry protects the Dirac knot degeneracy at the surface of an IFM TI. If this surface is preserving this symmetry, it is going to be gapless, while it will be gapped at this S-breaking surface each and every time when there is a non-zero magnetization component perpendicular to it. And this is the most interesting case because such a system would have an electromagnetic response characteristic of a so-called action insulator. And as of middle 2018, there was no AFM-TI confirmed experimentally. Until we have found this manganese bismuth tellurium 2-tellurium 4 guy, MBT, which was first synthesized in 2013, but in the powder form. Actually, the focus of this this study was the thermoelectric performance of the material. Therefore, they did not really study the magnetism or electronic structure, but of course they characterized the crystal structure by X-ray diffraction, and they found that this material is a block layered van der Waals compound made of septuple layers with manganese layer in the center of the block, and the blocks are held together by van der Waals forces. So you can see that this material is pretty similar to bismuth telluride, which is a canonical non-magnetic topological insulator. So we accepted the challenge of studying this material by using DFT, which is our specialization. It was not easy because nothing was known from the experimental point of view, so we had to be very careful. We started our investigation by calculating the magnetic properties, in particular using Heisenberg exchange constants calculations for both intra and interlayer exchange couplings, these red and blue guys here. You can see here that this J01 parallel shows strong tendency for the ferromagnetic ordering inside the manganese layer, but somewhat more complex situation is observed for the interlayer exchange coupling. But if you analyze it carefully and you take into account as many neighbors as you can, actually we have taken into account, I don't know, maybe 50 neighbors, but actually this would be the leading one. You will end up with a conclusion that it is an antiferromagnetic interlayer exchange coupling, as it is shown here. On top of that, we have calculated the magnetic anisotropy, and we have found that the easy axis points perpendicular to the manganese layers. Okay, and this is the mechanism of the magnetic ordering, which is Anderson super exchange here. So the next question to be asked is whether this material is S-symmetric. Let us consider this. In the non-magnetic case, this T1/2 primitive lattice translation is obviously a symmetry, but it is not in the antiferromagnetic one. Because if you take this manganese atom with the spin looking down, you translate it here, all spins are looking upwards there. It's not a symmetry. But if we apply the time reversal symmetry operator afterwards, we flip the spins, and this is how we nicely recover this antiferromagnetic structure. So the answer is yes, it is asymmetric. Is it an insulator? Yes, the bandgap is about 220 milli-electron volts according to our calculations, and therefore it falls under the Z2 topological classification. We therefore can calculate the Z2 topological invariant based on the parities of the occupied bands. And this is how we end up finding that the Z2 is equal 1, basically means that this is topological material. Its bandgap is therefore inverted, which we show directly by calculating the density of states, starting from the natural value of the spin-orbit coupling constant lambda 0, and then we go decreasing it stepwise. We see that the gap is closed and then it reopened. So this is the bandgap inversion. Therefore, we can conclude that this material is a three-dimensional antiferromagnetic TI. This means that it should have the termination-dependent surface states. And of course, it does, because at this 0001 surface, which is S-breaking, we see the Dirac point gap of about 90 milli-electron volts, which is due to the perpendicular magnetization of the manganese layer near the surface, while this S-preserving surface with these weird indices, basically this is the side surface, like that, is gapless, as it should be for the antiferromagnetic TI. Of course, our colleagues have synthesized then the single crystals, and they were thoroughly characterized. Vladislav told us already a lot about this, about electronic properties and magnetic properties. Basically, a lot of things have been confirmed in the experiment. Therefore, I proceed with the theory. Let's go into the two-dimensional limit and consider first the magnetism and then topology. In case of the magnetism, basically nothing unexpected happens, because a single septuple layer block preserves its ferromagnetic nature. Once we have more than one, we have antiferromagnetic interlayer coupling. I would like to just emphasize that for the even number of blocks, I will call this structure compensated antiferromagnetic one, and for the odd number of blocks, I will call it uncompensated one. This will make the huge difference for the topology, as you will see just in a moment. So we characterize the topology. Single septuple layer has Chern number equal to 0, meaning that it is trivial ferromagnetic insulator. Then we go for the double septuple layer block, and we get the Chern number 0 again. Kind of very boring, but this is actually not the end of the story, because if you calculate the ferromagnetic state for this film, which you can always achieve in the experiment by applying external magnetic field, you have Chern number equal to 1, which is the Chern state or quantum Hall insulator state. This actually means that in its magnetic ground state, which is compensated antiferromagnet, this system is nothing but zero plateau quantum anomalous Hall state, which is an intermediate state when you go from the magnetization up, Chern plus 1, to the magnetization down, Chern minus 1, through the intermediate state here with Chern equal to 0. Why I'm being so annoying about this? Because such a state has been predicted to show electromagnetic response characteristic of the axion insulator state. So then we go for the 3 septuple layers. We have quantum anomalous Hall insulator intrinsically without need of applying external magnetic field. And then it goes in a kind of oscillating fashion, because for even number it is zero plateau, and for odd number of blocks it is quantum anomalous Hall effect intrinsically again. And we were very happy to see all these predictions confirmed experimentally very soon after. This zero plateau quantum anomalous Hall state was reported in 6 septuple layer thick film of MBT in this Nature Material paper. They call it directly axion insulator. Then they apply the external magnetic field, and they have the ferromagnetic polarization in the film, and they observe the quantized Hall conductivity. But this is actually not exactly as in the case of von Klitzing. This is under external magnetic field as well, but there are no Landau levels involved. So this is a kind of new type of Chern insulator, if you wish. And a similar result was achieved by Denk and co-authors, who has actually been able to realize truly intrinsic quantum anomalous Hall effect, meaning that the resistivity is now quantized without external field, as you can see here. Also, I would like to advertise the results by other group who realized the high Chern number and high temperature states in the MBT films up to 30 Kelvin or 10 Kelvin for the Chern 2, Chern 1. So this is all very remarkable. So as you have already seen, MBT appears to be a promising platform for a number of Hall effects. Actually, 6 of them are claimed to be observed, and still we have 3 pending, maybe more, who knows. Shown here on the left is the artistic representation of the half integer quantum Hall effect. So very rapidly, the current status of the field. Very soon after the MBT has been reported as antiferromagnetic TI, there appeared very intense discussion of whether this material has gapped or gapless Dirac cone. First, synchrotron radiation ARPES studies reported gapped cone, but the following laser ARPES, which gives you a way better resolution, you can see that the image quality is much higher. They reported in numerous occasions the gapless cone, which contradicts completely the theory. And a number of possible explanations were proposed. From my point of view, none of them has sufficient basis beyond. So in relation to all of this, I would like to tell a number of things. First of all, even with laser ARPES, you can have a gapped Dirac cone, as it is shown by the extensive study by Alexander Shikin group from St. Petersburg. You have here 15 samples of MBT grown by different chemist groups. This triangle means different chemist group. And basically, the conclusion is that you can have any value of the gap starting, let's say, basically from 0 up to 65. So the cone is not always gapless. It depends on the sample. So why can it be gapless or gapped? Of course, I do not have the final answer to this question, but I will try to argue. Recently, we have learned that the saturation magnetization for the magnetic moment of manganese in MBT is about 50 Tesla, which is a huge field. And only then it reaches about 4.6 Bohr magnetons, which is in agreement with prediction by DFT, and this is something which you expect for manganese 2 plus, spin 5 halves. Why does this happen? The interpretation is that due to the manganese bismuth intermixing, there is a cation intermixing between these 2 species. manganese atoms incorporated in bismuth layers, they couple antiferromagnetically to the central layer of manganese. Depending on the sample, depending on how you determine this concentration, depending on the model you assume when you fit your XRD data, you can have in between 1 and 9% of manganese bismuth atom. If you calculate the concentration based on the STM, typically it doesn't exceed 5%. Looks kind of incredible. Could this be the reason? Actually, this is the only structural imperfection that has been confirmed by the community. None other defects exist in this material, at least as confirmed and firmly established. So we have started with an idea of checking, first of all, the topological surface state distribution near the surface. This is the charge density in the real space. And we have found that actually it has a minimum in the manganese layer. There is a lot of manganese, a lot of magnetization, but there is a few topological surface state charge density. And actually the maximums are near the bismuth layers. And it is exactly where you put these manganese atoms. So we have decided to perform the direct calculation. This is the ideal case, 90 millielectron volts. And then we put 10% of manganese into the second layer. We see more than twice reduction of the Dirac point gap. But this is not the localization of the maximum charge density. The maximum is here. We put 10% here, and we see 3.5 millielectron volts. It is gone. Here, the scale is different. Okay, this is 3.5. Is this the final answer? I don't know, but there is something to it. This is the real effect, at least. So yeah, and probably if we are able to suppress this cation intermixing, we will likely enhance the quantum anomalous Hall observation temperature, which is currently at 1.4 Kelvin. I expect that we could go much higher. So if I still have a bit of time, a bit more about on the progress. So actually, starting from this 1-2-4 composition, you can play a little bit with the structure, designing, and intercalate non-magnetic quintuple layer units in between two septuple layers. You can basically do as many as you can. At least experimentally now you can go up to 6 quintuples between two septuples. And depending on the number of them, you can realize different magnetic phases such as antiferromagnetic TI or partially disordered magnetic topological insulator, or even a ferromagnetic axion, which is some sort of high-order topological insulator state. These are the electronic structure of these materials, 147, 1610. Probably I don't have much time to go into details. I would like to highlight a recent result on the quantum anomalous Hall effect as well, achieved in this 110-16 phase. It is now increased the temperature 6.5 Kelvin, so hopefully we'll go even higher. And going a little bit to the past, we have actually predicted that these materials that are similar to MBT share the same crystal structure made of septuple layer blocks, and they actually have the same magnetic order. The funny thing about this material in particular, that in the experiment, the bulk single crystals are always monoclinic, which is this structure. But we have found that actually this structure, the layered one, is more favorable. So in principle, if you are able to grow it with an appropriate technique, it can exist. And this was confirmed very recently in the experiment. You see this van der Waals layered structure. It has been confirmed as an antiferromagnet, but it has in-plane magnetic moments. So, and you can see this Dirac cone. And actually, for the TIs like those, you can have, due to the in-plane magnetization, these topologically protected flat bands at the surface, exactly pinned to the domain walls, separated two domains with the opposite direction. And also, this guy has caused a lot of debate, because many groups predicted that it is topologically trivial. We actually predicted it is topological, as it is shown here. Basically, the trick is simple as carefully optimizing the material, but actually it has received very recently the experimental confirmation of the non-trivial topology. So with this, I would like to thank all the collaborators. There are many, both theorists and experimentalists. In particular, Vladislav has helped us a lot with ESR measurements. And yeah, these are my take-home messages on MBT and related materials, and I would be happy to answer your questions. Thank you very much.
So thank you very much for a very interesting presentation of the recent insights into the theory of these materials.
Actually, my question is about the first part of your talk. It's about time reversal symmetry. Well, I think that, well, if you work on particle physics or high energy physics, then you should think very seriously about this and include some terms in your Hamiltonian. But you are working in solid state physics. In solid state physics, I think you work with thermodynamics. And in thermodynamics, the time reversal symmetry is broken by the second law of thermodynamics, you know. And I think
there is no thermodynamics in DFT calculations.
Why? So you don't care temperature?
There is no temperature. We work at zero temperature. So
how can I imagine that you have a lot of particles and there is no statistics, no thermodynamics?
As strange as this, but we work at 0 Kelvin, and we are able to produce something which is later on confirmed experimentally. We typically do not dare to discuss, let's say, high temperature phases, unless we are talking about Néel temperature. But if we are talking about Néel temperature, we're talking about magnetic material. And magnetic material, the time reversal symmetry is explicitly broken. It is preserved if we are talking about, let's say, bismuth selenide or bismuth telluride, which is the non-magnetic material. Yeah, there it is preserved, and since there is no thermodynamics, there is no temperature, there is no time reversal symmetry breaking.
I understand. Thank you.
Thank you very much.
So there is a question in the chat. Can you please elaborate what is the signature of the axion effect? Please do that in a few sentences, if it's possible.
Yeah, thank you very much for this question. Actually, it sounds quite fancy, I admit, but the way I see this is a simple analogy with the, let's say, particle physics, because the magnetoelectric response of the topological insulator from its bulk has the same, exactly the same effective action as the axions, like identical, and what is called theta magnetoelectric polarizability in a solid state, and there in axion physics, let's say it's axion field. But there is more to it. If you are interested, please just do your own research about the topic, because I'm the computational material scientist. I'm not high energy physicist, but there is more to it. People are studying this, so please look for the literature.